This video is all about dimensionality and table 23 in Winsteps. So when we think about dimensionality, it's not quite the hard and fast rule, which is just like exploratory factor analysis. We had lots of different pieces of evidence, and holistically, we use those to make the best decision on how many factors we're going to retain. Not surprisingly, Roche is the same way. So we have two things specifically that we're going to look at, overall fit, and then really specifically the principal component analysis of residuals. That's what's in table 23. There are also times where we can look at person and item fit separately, but we don't really use it as an appraisal. It's more like which gives further support of model fit, because if those fit and everything else is working well, then it's showing that the model is fitting well. Lineker does say that multidimensionality is usually too vague to show up in specific item level or person level fit statistics. But if you have an item that doesn't fit well, it actually could potentially affect your dimensionality. So they do kind of go hand in hand, and we take this holistic approach. So overall fit is in table 3.1. There's a whole other video on 3.1, which we'll go deeper into. But we're looking at the overall mean square, MNSQ. We want that to be around 1. We're also going to look at the overall standardized fit, which is our ZSTD. It's going to be around 0. How close to those values? As close as possible, but generally MNSQ values, mean square values, between 0.5 and 1.5 are considered to be productive of measurement. So those are kind of your boundaries for the mean square. This is what table 3.1 looks like, and that's where we're going to find those. So in that very first top line, we can see 0.85 and 0.87 for the mean squares. Not as close to 1 as I would like, but it is still within our range. And then the standardized is negative 0.3 and negative 0.2, which are pretty close to 0. All of this is based on principal component analysis of residuals. We have seen PCA before when we did the EFA analysis. We're now doing PCA on residuals, which is different, and that's PCAR. So this examines patterns in the part of the data that is not explained by the Roche dimension. So the Roche dimension is the first dimension. And what we do is we pull out that first dimension, and then we look at the residuals, and we see if in this extra noise, once we remove that first dimension, do we see patterns in the noise that are enough to give us a hint of the second dimension? And the question is the second dimension large enough to matter? So this is kind of like EFA, where we would have kind of our rotated components matrix. So this first one would conceptually be our Roche dimension, and then we're seeing, are these extra ones enough, do we see enough pattern in the residuals to call these a second factor once we have removed the Roche factor, which is that first one. The difference is with EFA, we're looking at correlation-based things, and here we're actually looking at residuals. So if we think back to regression, we looked at all of the residual plots. That's how far everything is from the line of best fit. In this case, it would be the Roche model and how far everything are kind of, falling within those residuals. So Lineker's approach is perform your Roche analysis. The Roche dimension is the first factor. The first factor in the residuals is conceptually the second overall factor. So that first contrast is what we're going to call it, is the first factor in the residuals once the Roche dimension, which is our true first factor in the unidimensional construct we're trying to understand, is removed. And so we're trying to see, once we remove that, is there enough stuff left over to call it a second dimension? Here's the rules. We want the variance explained by the Roche dimension, that first dimension, to be above 60. And then we want the eigenvalue of the first contrast, which is conceptually the second dimension, to be less than 2 and have 2 items to explain it. And then we want the variance explained by the first contrast to be less than 5. Except that's sometimes too strict. And so explaining 40% of the variance is also acceptable, especially for shorter measures. Lineker actually has emailed and talked to us about if you have 20 or fewer items, then 10% unexplained variance in the first contrast can be expected. And it's really not the percentage that's important, it's the size of the eigenvalue. So we really want that to be below 2 Although again, shorter measures can have eigenvalues a little above 2 as long as they're below 3, according to Bond and Fox. So we're taking this holistic approach to really understand and clean up our measure because we need it to be unidimensional. We don't want other noise in our model that is going to affect the ruler. We don't want to measure two things that are clumped together that need separate rulers. So you want to clean everything up to have a clean ruler. So generally speaking, dimensionality rules, if the eigenvalue is less than 2, then we consider the second dimension to be random noise, period. If the eigenvalue is more than 2 and has 2 items loading onto it, then we start to be concerned. So PCAR is indicative but not definitive about that second dimension. Hence, we can have eigenvalues with more than 2 and around 10% if there's only one item or a few other situations that you'll be able to see. So here's what table 23 looks like, a portion of it. So we have the raw variance explained by the measure, in this case 39%, not quite 40 but close. Then we also get to break it down by items and by persons. We think back to ANOVA. ANOVA looks at variance in 2 ways, between group and within group. We're essentially doing the same thing. We're looking at variance explained by person and variance explained by item. And then at the bottom here, now we have our unexplained variance in the first contrast. So this is the eigenvalue for our second dimension. So our eigenvalue right here is 2.6. That is larger than 2. I don't like that. And I'm explaining a decent amount. I'm explaining 13% of the variance based on this second dimension. So in that case, I'm going to want to look deeper. If you want to try to make the argument that that is not a real dimension, probably you're going to have a hard time with this one. And especially if you find something like this, where we're picking up a factor for the first contrast, a factor for the second contrast. We've got potentially 4 extra factors in the noise after the Roche dimension has been removed. So this is explaining up here, is explaining the Roche dimension, conceptually the first factor, and picking up 4 potential extras. You're not going to have any dimensionality argument if you see this. Okay, so here's our full table. This is indicating that we have 5 items, so it's a small measure, but it's explaining 84% of the variance. That's huge. 77% is coming from persons, only 6% is being explained by items, which is a little concerning. So here we have an eigenvalue of 1.8, so that's below 2. I'm just going to stop right there and say it is not showing a second dimension. Even though it's explaining 6%, which is higher than our 5%, the eigenvalue kind of trumps that, and we're happy. So I'll let you pause the video and look at this one. So here we have 18 items. This is an old version. I don't know what TAPS used to be called. Here we're explaining 99.6, almost 100% of the variance, which is crazy, by the measure. And then our first contrast is 2.7, which is definitely showing potential of a second dimension, but it's not explaining anything at all. So I'm not as worried about this. I'm explaining so much of the variance based on the measure. This second, these 2 contrasts, I want to look deeper and see what they're saying, but that I'm less concerned with. Also explaining that much variance is unusual. So here is a more typical thing that we're looking at. 18 items. We're explaining 36% of the variance, so not a lot, which is concerning. And we have everything kind of right on the cusp. So we have a 2.1 eigenvalue, which is higher than 2. And it's explaining 7% of the variance. I don't know about this one. I definitely am going to have to look deeper and see what's loading onto that second dimension, and does that seem real? Here's another one that I will let you pause the video and look at. So here we're explaining 66% of the variance by the measure. We're explaining 55%, almost 56% based on person, and only 10% based on items. And then I have my unexplained variance in the first contrast. This is my eigenvalue for that second potential factor is a 2.2. That's concerning. And I'm explaining 15% of the variance in that kind of potential second dimension. This one I definitely need to look deeper at, but there's another thing happening here. My second dimension, which is essentially patterns in the noise, is explaining more than my items in my Roche dimension. That is a huge red flag. So I want my measure to be explaining more than the noise based on the items. Definitely got to figure that one out. If you scroll down in table 23, you can get to 23.2, which is up here. And you can see that these are the items that are loading onto the Roche dimension, and then these right here are the ones that are loading onto some other dimension. So that's what's being pulled out in the second dimension. The one that I just showed you that's explaining more variance in the noise than it is the items is right here. So we can see that 3 of the items are grouping together on the Roche dimension, and there's one right here that's grouping on its own. And that's the problem item as far as dimensionality. It may not be a problem item that you pick up in the item fit table in table 10, but in dimensionality, this is where your problem is coming from. It is only one item, so you could make the argument that it's okay to keep, but it's explaining so much of the variance on its own that you got to figure out what's going on and why that could be a problem. So generally when we think about this process, you check table 23 and then table 3.1. If the results don't meet the criteria, then scroll down to that table 23.2 and look at your first contrasts and see what is loading where. Then check all of your other tables. So check your item table and person table, see if you have any extreme outliers and misfitting persons or items. That could be picking up in dimensionality, but not always. What I do see that really affects it is categories. So if you have a scale that's just really not working, that's where you need to start fixing first. Because you have to fix dimensionality before you can fix everything else. And everything still goes hand in hand because, of course, you change one thing in the matrix and the whole thing changes. So I want you to go through a couple of the examples that are posted or on your own if you are not in my class, and try out some stuff. Check out table 23. If you are using my things, these are kind of the answers and the things that I was seeing.